let's look at some of the terminology that we use when we deal with circle geometry. You have the circle given here. This outer part of the circle, we call it the circumference. This is the circumference of the circle. This is the center of the circle. So if I draw a line from the circumference through the center to the other circumference, we call that line a diameter, right? So it goes through the center of the circle. But if I draw a line, any line, anywhere, that goes from circumference to circumference, but it doesn't go through the center, we call it the chord. So any line from circumference to circumference that doesn't go through the center, we call it the chord. If you draw any line from the center to the circumference, it doesn't touch the circumference in two places, we call that line the radius. So this is the radius of the circle. It just moves from the center to the circumference, right? And the plural name for the radius is the radii. The radii of a circle are all equal. So this is the radius of the circle, this is the radius of the circle, and that is the radius of the circle. It moves from the center to the circumference, center to circumference, center to circumference. They are all equal. So if this is 5 centimeters, that will also be 5 centimeters, and that will be 5 centimeters. The radii of a circle are all equal. Now let's look at another line which only touches the circle once outside the circle. So at the circumference it touches the circle once. We call this line a tangent. So a tangent only touches the circle once. Any portion of the circle is called an arc. You will see we will be using this. So from this portion all the way to here, this is an arc of a circle. That piece there is an arc of a circle. This is an arc of a circle. This red line over there is also an arc of a circle. Any portion of a circle is an arc. That's it. Now let's look at theorem number 1. The theorem number 1 says a line from the center of the circle, which is perpendicular to a chord, bisects the chord. So if we have a line that moves from the center of the circle and then it makes an angle of 90 degrees with any chord, by the way, in this case we have chord AB or AMB. So any line that is drawn from the center of the circle and it's perpendicular to the chord, it bisects the chord. So by bisect we mean that it divides the chord into two equal halves. That means since OM is perpendicular to AB, therefore AM equals to MB. What is the reason that we use for this? Line from center perpendicular to chord. Now this is important, the issue of reasons. The next part we will be solving riders that rely on these theorems. So each time you mention a theorem as evidence of that answer that you have for the rider, you have to show them the reason. You have to show which theorem actually you used to arrive at that particular solution. So when you are using theorem number 1, normally this is how we summarize that statement, the line from center perpendicular to chord. It should make sense, right? Now let us look at the converse of this theorem. The converse says a line from center to the midpoint of a chord is perpendicular to the chord. Here we said if a line is perpendicular to the chord, then it bisects the chord. Now if that line moves from the center of the circle to the midpoint, or it bisects the chord, therefore that line is also perpendicular to the chord. And this is the reason that we use line from center to midpoint of chord. It's simply to summarize this. You need to state the reason when you are solving a rider and then you find this theorem. You need to remember how to summarize that as a reason. I want us to look at an example 1, which involves this theorem. Say you're given here a circle with center O, so O is the center of the circle there, and we're given that AB is equals to FD, they are all equals to 8 centimeters, or F is X and it's shown there, we are required to calculate the length of the radius of the circle. We know that the radius of a circle is any line that moves from the center of the circle to the circumference. So OB is the radius. OF can't be the radius because it doesn't go all the way to the circumference. OD is the radius because it moves from the center to the circumference, right? So where do we start? We know that AF should be equals to FB. Why? We remember that any line drawn from the center of the circle, which is perpendicular to any chord, it bisects the chord. Therefore, since we know that AB is 8 centimeters, then AF would be 4, FB would be 4. This is a half of 8 because OF cuts AB into 2 equal halves, and AB is 8 centimeters. This is the reason. There isn't a line from center perpendicular to chord, so you need to know to show which theorem you use to arrive at this particular point. Now we know that the radii of a circle are equal, therefore OD and OB should be equal in length, right? Now, how can we express the length of OD? We know that FD is 8 centimeters, OF is X. Therefore, to find OD, we can simply say 8 minus this in order to find the length of OD. So OD will be 8 minus X, and we know that it is equals to OB. So OB and OD are the radii of the circle, and the radii are equal, right? So we have that the radius of the circle at the moment is represented by 8 minus X, 8 minus X. In this triangle OBF or FBO, we have a right angle triangle and we have all these 3 sides. We can use the theorem of Pythagoras to actually calculate the value of X by simply substituting the values that we have, expanding, and then we find that the value of X is 3. Then we can simply substitute the value of X in any of these to find the length of the radius. Therefore, the length of the radius, I just choose OB, it's 5 centimeters. We are going to skip theorem 2 because theorem 2, it's simply a proof. You hardly find it in riders. It says that the perpendicular bisector of a chord passes through the center of the circle. So you may just be required to prove that, and I am not covering proofs in this part of the lesson. So let's look at theorem number 3. The theorem number 3 says an angle subtended by an arc of a circle at center is equals to twice the angle subtended at the circumference. Remember, we said, so I have this arc. We said the arc is a portion of the circle. I have the arc AB, which subtends this angle here, AOB. So this arc AB subtends AOB over there at the center. It also, this arc AB subtends this angle C, ACB, right? So what this theorem says is this angle that is subtended by arc AB at the center is 2 times this angle here. So if I have 20 here, this angle will be 40. If I have 50 here, this angle will be 100. If I have 100 here, this angle will be 200. So the angle at the center is 2 times more than the angle at the circumference. So you need to be able to see this kind of theorem in a problem because you won't be told that. So you see how it looks like, right? And all the vertices of this shape are touching the corners of, they are touching the circumference of the circle. That's very important because you might have a shape like this, but you find that it doesn't touch some parts, it doesn't touch the circle, or maybe it's even outside the circle, so you can't use that. All these vertices must be touching the circle. So the angle at the center is twice the angle at the circumference. We have this diamond shape here. We have the arc AB. This is a bigger arc, you see it, that bigger arc subtends this angle AOB at the center. It also subtends that angle, the same arc. It also subtends that angle C, ACB at the circumference. So this angle over here is 2 times that angle. If this angle here is 130, then this angle here will be 260. If that angle there is 100, this angle here will be 200. So the angle at the center is 2 times the angle at the circumference. So this is what we are showing here, that AOB, angle AOB is 2 times angle ACB. So this angle here, right? Let's look at the third version of this theorem. We have the arc AB. This arc subtends this angle at the center, and then it also subtends this angle at the circumference, right? So this angle will be 2 times that angle. I have the arc AB, which subtends that angle, and then it subtends that angle. So if this is 40, this will be 80. If this is 10, this will be 20 degrees. If this is 40 degrees, that will be 80 degrees. The angle at center is 2 times the angle at the circumference. Let's look at the special case of this theorem. The special case of the theorem, it's when you've been given a diameter of a circle, right? We said the diameter is any line that passes through the center, goes from circumference to circumference. This is a special case. We call it angles in a semicircle. An angle subtended by a diameter at the circumference is 90 degrees. You can prove that using the angle at center twice the angle at the circumference. We know that angles along a straight line add up to 180. So this would be 180 degrees. And then that should be half of 180 degrees, which is 90 degrees. And this is the reason that we use for this theorem, right? We say angles in a semicircle. So that will be the reason that you use. So C here, or ACB, will be 90 degrees, right? So let's have a look at a quick example here. We are given that O in both, O is the center of the circle. Determine the values of X, Y, and Z with reasons, right? So let's start with this one. I said if you have this shape, right, with all its vertices touching the circumference, then the angle at center will be 2 times the angle at the circumference. That means since I have 100 here, what will be the value of X? The value of X will be half of that. Remember, the angle at center is the biggest than the angle at the circumference. So if I have 100 at the center, I should have 50 at the circumference, right? Let's try Y. Remember the diamond shape that we dealt with. We said if you have this diamond shape, then the angle at center will be 2 times the angle at the circumference. The only part that we don't have now, the angle at center that we're talking about, the 100 that we have, doesn't really match the theorem that we have. But we know that we can find the angles around a point. We know that angles around a point add up to 360 degrees. So we can find this portion, the O1. We can find O1 by subtracting 100 from 360. Give the reason a revolution. We normally use the revolution as the reason for angles around a point, right? So which means O1 will be 260 degrees. This is the angle at center that we're interested in. So 260 is 2 times Y. That means Y is half of that 260 degrees, which is 130 degrees, right? Let's come to this theorem. Remember, we have the arc AB. We have the arc AB. This arc AB subtends this angle at the circumference, and then it subtends that angle at the center, right? So here we know that Z is 2 times C2. But what is the size of C2? O is the center of the circle. If O is the center of the circle, then DB is the diameter. An angle subtended by diameter is 90 degrees. If this is 90 degrees, we have 70, then it means C2 will be equals to 20 degrees, right? C2 will be 20 degrees. This we find that C2 is 90 degrees minus 70. These are angles in a semicircle, and then C2 will be 20 degrees. We know that the angle at center is 2 times the angle at the circumference. So if the angle at the circumference is 20 degrees, then Z should be 40. What is the reason that we use? Angle at center equals to 2 times the angle at the circumference. So Z will be 40 degrees. Let us look at Theorem 4. Theorem 4 says, if the angles subtended by a chord of the circle are on the same side of the chord, then the angles are equal. We simplify this by saying angles in the same segment are equal. Let's say this is the chord. Normally, this statement chord there, we could also use the word arc, right? We could say if the angles subtended by an arc of the circle are on the same side of the arc, then the angles are equal, right? Let's say we have this arc DC here. You see, the arc DC subtends the angle B. It also subtends the angle A at the circumference. You must be very careful. You see this butterfly shape. All the vertices must touch the circle. All the vertices must touch the circle. If you remember, the angle at center equals to 2 times the angle at the circumference. Let's have a look at it. You see this theorem here. It looks like that fourth theorem that we are dealing with. But if you look at this, only 3 vertices touch the circumference of the circle. This one touches the center of the circle. So you can't use the angles in the same segment with this one, because this vertex here doesn't touch the circumference of the circle. It's only when the vertices touch the circumference of the circle that we can use angles in the same segment, right? So DC is our arc. This arc subtends A at the circumference. It also subtends B at the circumference. Therefore, A will be equals to B. These are angles in the same segment. This is the reason that you give angles in same segment, right? Similarly, the arc AB. The arc AB subtends the angle C at the circumference. It also subtends the angle D at the circumference. Therefore, D equals to C. These are angles in the same segment. So this is the reason that we use angles in the same segment. Now there are special cases for this theorem. If I've got 2 equal chords, it doesn't matter where they are. If I have 2 equal chords, those chords will subtend equal angles at the circumference, right? So this chord equals to that chord. That means this angle will be equal to that. So equal chords subtend equal angles at the circumference, and they also subtend equal angles at the center. So if I have a chord that subtend an angle at the center, and I have another chord that subtend an angle at the center, and the 2 chords are equal, then these angles will be equal, the angle at the center. So equal chords subtend equal angles at the circumference and at the center of the circle. Let's have an example. We are given that O is the center of the circle. We are also told that AB, the chord AB, is equals to the chord DC. And then we are given the angle AEB equals to 39 degrees. The question is determine the length of O1 and the length of O2. Look at the arc AB. The arc AB subtends the angle O1 at the center, and it subtends the angle E at the circumference, right? So this is the angle at center twice the angle at the circumference. You need to be able to see this. If you look at it, this is the one. It's the arc AB, or the chord AB. It subtends this angle at the circumference, and the same arc subtends this angle at the circumference. So the angle at center twice the angle at the circumference. If I have 39 there at the circumference, so here I must have 2 times 39, which will give me 78 degrees, right? The reason is angle at center twice the angle at the circumference. Don't forget to put the reason. Show us which theorem you used to arrive at that particular solution. So the theorem is angle at center equals to 2 times the angle at the circumference. So O1 is 78 degrees, right? O2 will also be 78 degrees. What would be the reason, right? We are told that chord AB equals to chord DC, right? Equal chords subtends equal angles at the circumference. Therefore, O1 and O2 will be equal because they are subtended by equal chords at the center, right? So O2 is also 78 degrees. Equal chords subtends equal angles at the center. Right, let's look at Theorem 5. Theorem 5 deals with the cyclic quadrilaterals. Quadrilaterals are four-sided shapes. Right. So when we say something is a cyclic quad, we are simply saying it's a quadrilateral whose four vertices touch the circumference of the second, right? So if you find any four-sided figure whose vertices touch the corners, okay, it touches the circumference, or yeah, touches the circumference of the second, then you have a cyclic quad, right? So the first theorem, in fact, the only theorem that we have in this is that the opposite angles of a cyclic quad are supplementary. The statement supplementary means that they add up to 180 degrees, right? So the angles that face each other in a cyclic quad will always add up to 180 degrees. Right there, you find a rider, and there's a four-sided figure whose vertices all touch the circumference of the second. You know that A plus C will give you 180 degrees. What is the reason? Opposite angles of a cyclic quad. B and D added together will give you 180 degrees. These are the opposite angles of a cyclic quad. So the opposite angles of a cyclic quad will always add up to 180 degrees. So another thing that we know about cyclic quads is that an exterior angle of a cyclic quad will be equals to its opposite interior angle, right? So if I have an exterior angle, and you must be very careful of this, because this line that is protruding out, it must be the same, like it must be an extension of one side of that cyclic quad, right? Because you can have a line that goes this way, which doesn't really which is not a continuation of any side of this cyclic quad here, right? First, why do we say this is a cyclic quad? All the vertices of this quadrilateral are touching the circle, right? And then I've got one side which protrudes outside, and then the angle made by that line that protrudes outside, or that side, and the other side. So this is the exterior angle. So that's very important, that this must be the same side, just extending outside. So the angle made by this will be equals to the angle made by the angle in the interior opposite side, right? So this will be equals to that. If this line could extend further, right, this angle here will be equals to that. If I had this line going all the way up, this angle here will be equals to that. So an exterior angle of a cyclic quad is equals to the opposite interior angle. So okay, this was written the other way around. Let's have a quick example of this. In this case, we have to calculate the values of x, y, and z. All right? We have to calculate the values of x, y, and z. Now, to find the value of x, we know this is a cyclic quad. How do we know that? We know because A, B, C, and D are all on the circumference of this second. So this four-sided shape, it's a cyclic quad because all its four vertices are touching the circumference of the second. That means A plus C should give me 180 degrees, right? So A plus C, which is 110 degrees, plus X should give me 180 degrees. What is the reason? The opposite angles of a cyclic quad, which gives the value of X to be 70 degrees. Similarly, B plus D, which is 100 plus Y, should give me 180 degrees, right? Which gives the value of Y as 18, right? In this case, I've got a line that protrudes outside, and it makes that angle with one other side. This is an exterior angle of a cyclic quad. An exterior angle equals to the opposite interior angle. Therefore, Z will be equals to 60 degrees. The exterior angle of a cyclic quad. That would be a good reason enough. So you just say exterior angle of cyclic quad. Okay, now let us look at one important part. I'm telling you, when you solve the riders in Euclidean geometry, you are, I can assure you that you will meet a question of this nature, where you are required to show that a particular four-sided figure, it's a cyclic quad, right? The first thing, such a shape or whatever figure that will be given to you, it will not have all its four vertices touching a circle. So they would want you to prove that if this was inscribed in a circle, it would meet the requirements of a cyclic quad. So it won't be inside a circle, like we know that, okay, because automatically if all these vertices, if P, S, R, Q are touching the circumference of a circle, automatically that is a cyclic quad. But then you find that you have a shape, and this shape, it's four-sided, of course, but the vertices are not touching the circumference of the circle, and they say to you, prove that PQRS is a cyclic quad, right? So what they want you to do is, if you can show that P plus R add up to 180, you would have proven that it is a cyclic quad. So if its opposite angles add up to 180, and you don't need to show all the opposite angles, you just need to show one pair of opposite angles. If you say P plus R and then it gives you 180 degrees, then you can say then PQRS is a cyclic quad, and then also give a reason, right? It's very important to give a reason. They say prove that PQRS is a cyclic quad. You are going to use other theorems, and then whatever else you know, maybe the properties of straight lines or properties of triangles, to prove that P, when added to Q, gives you 180 degrees. If you do that, then you say, okay, I've shown that P plus R equals to 180 degrees. Therefore, PQRS is a cyclic quad. You need to write that statement. You can just say PQRS is a cyclic quad, and then give the reason. Opposite interior angles are supplementary. And then in some situations, you find that, of course, you do have the shape that is given to you. Like I said before, PQRS will not be inscribed in a circle. So these vertices will not be touching the circumference of a circle in that situation. And then you find that, of course, you have one line or one side that protrudes outside. If you can show that R1 equals to P, if you can show that an exterior angle equals to the interior opposite angle, then you would have proven that that particular shape is a cyclic quad. You only have to prove one of that. You either prove that the opposite angles are supplementary, or you prove that an exterior angle equals the opposite interior angle. Then you can say, okay, therefore PQRS is a cyclic quad, and give a reason. The reason is that the exterior angle equals to the interior opposite angle, right? And then in some situations, you find that the shape they want you to prove looks like this. Now, one thing that I must tell you, if PQRS are all touching the circle, this is a cyclic quad automatically, so there's no need to prove it. Then the challenge is, you find that when they give you this shape, it's not inscribed in a circle, but they want you to prove that it is a cyclic quad. So what they want you to do in this case, they just want you to prove that P, remember angles in the same segment, if you can prove that P equals to Q, you are done. If you prove that S equals to R, then you are done with what they want you to do, right? So in this case, if you were to prove that P equals to Q, or you prove that S equals to R, then PQRS will be a cyclic quad. What would be the reason? Angles in the same segment equal. So if you can show that the angles in the same segment of any four-sided shape are equal, then you have proven that that shape is a cyclic quadrilateral. Right. Okay, let us look at problem, okay, an example 5.1, right? If you look at that problem, you are given a circle, and then you've got E equals to 90 degrees. So those are the obvious things that you can see. O is the center of the circle. Even though that statement is not written here, O is the center of the circle. You've been given 90 degrees there. You are required to prove that A, B, D, E is a cyclic quad, right? This is what I was talking about. If you look at A, B, D, E, this is not inside a circle, but they want you to prove that this is a cyclic quad. What can you do in this situation? Well, there are two ways we could do this. If you look at A, B, D, E, it is one side that protrudes outside. So if we can show that this angle equals to that angle, we will be done. If we can show that this angle equals to that, we would have shown that the exterior angle equals to the interior opposite angle, right? Let's start. We can show that CBD is 90 degrees. Why? I just said that O is the center of the circle. Therefore, DC is the diameter of the circle. An angle subtended by a diameter equals to 90 degrees. These are angles in a semicircle. So this angle here, CBD, is 90 degrees, right? And then E is 90 degrees. It's given to us. Therefore, ABDE is a cyclic quad. What is the reason? The reason is that an exterior angle, we found that this exterior angle here equals to the opposite interior angle E there, right? So we have proven that ABDE is a cyclic quad, but ABDE was not inscribed in a circle. The vertices of ABDE were not touching any circle, right? So we just had to show that ABDE qualifies to be a cyclic quad because its exterior angle equals to its opposite interior angle. Right? We could also have done this differently, right? Let's say we could say a CBD is 90 degrees, like we've shown up there. That is this is the angle in the same second. And then we can also show that ABD, this angle here, will be 180 minus 90 degrees. These are angles on the straight line ABC, right? So we know that angles along a straight line add up to 180 degrees. So if I have 90 here, obviously I will have 90 on the other side, so that they can add up to 180 degrees. Now, if E is given, it's 90 degrees, right? So if I add this angle here, A, B, D, and E, they give me 180 degrees, because E is 90, that one is 90, so they add up to 180. Therefore, ABDE is a cyclic quad, because its opposite angles add up to 180, or they are supplementary, right? So this is what I was referring to when I said the shape that they want you to prove is normally not inscribed in a circle. It's not inside a circle, but you just need to show that it qualifies to be a cyclic quad because, well, it meets the requirements. The opposite angles are supplementary, or the exterior angle equals to the opposite interior angle. One last part. You can also find that this is the third part of the proof, right? You find that, of course, you've been given this shape. They want you to prove that it is a cyclic quad. It is not inscribed in a circle. You just need to show that it qualifies to be a cyclic quad. What do you think we have to do in this case? Right. You have to show that A and B are equal. So you see we have this butterfly here, angles in the same segment. So if you can show that B here is 40 degrees, or we show that this angle here, ADM, is 32 degrees, we would have proven that this is a cyclic quad, because the angles in the same segment will be equal. So we would assume that DC is the chord that subtends that angle and that angle, or AB is the arc that subtends that angle and that angle. Therefore, if this is equals to that, or this is equals to that, then you have proven that this is a cyclic quad, because the angles in the same segment will be equal, right? Let's do that. We know that BMC is BMC, and this angle over here, BMC, will be 180 degrees minus 72. These are angles along a straight line. We know that they must add up to 180 degrees. So if we subtract 72 from 180, we should get the angle here, right, which is 108 degrees, right? In this triangle, BCM, MCB, however you call it, right, we already have this angle and that angle, but we know that the sum of angles of any triangle add up to 180 degrees. So if we add this angle and that angle and the angle B, we should get 180 degrees, because these are the sum of angles of a triangle, right? So at the end of the day, we have our MBC, which is the angle B, as 40 degrees. So we have shown that B is 40 degrees. Therefore, ABCD is a cyclic quad. Why? Because the angles in the same segment are equal. So if the angles in the same segment are equal, you have proven that something is a cyclic quad, whether it is inscribed in a circle or not, right? So what matters there is you being able to show that the opposite angles are supplementary, or the exterior angle equals to the opposite interior angle, or showing that the angles in the same segment are equal. So it's important. You have to show one of those, just one of those, then you have proven that something is a cyclic quad. So, but you find that it requires you to use other knowledge. You see, like we have used here the angles in a straight line, the sum of angles of a triangle, and in some point you might also have to use other theorems that you have learned previously. So you are allowed to use the other theorems that you have learned before, or the other theorems that you know, in order to prove whatever is required of you at that particular point. Now let's move on to theorem number 6. Theorem number 6 says that tangents drawn from the same point outside the circle are equal in length, right? So if we were to draw two tangents from the same point T outside the circle, and then this is the tangent AT and the tangent BT. These two tangents will be equal in length. It's very important because you find a situation where you are just being told that this is a tangent and that is a tangent and they meet here. You need to know, right? You need to know that, of course, from that point to here and from here to there, these tangents will be equal, right? So AT will be equal to BT. That is very important, right? So the reason that we use for that is that turns from same point equal. We are simply trying to summarize this, right? And I think you see the reasons that I've been showing you all around. You don't need to just cram them. If you find a nice way of summarizing the theorem that you know, I mean, in a shorter way, just to show that you know which theorem you used, that should work well. And then you should be able to get all the marks that you need, right? So, but the ones that I've used myself here, I've been following the question papers, and then it's just taking the way they reason from the question papers, simplify them the way they are. So, but it should work. It should work for you if you can summarize them in any way better, right? So this is the way you reason. So if you find that, okay, there are two tangents that were drawn from the same point outside the circle, and then you want to use that knowledge, this is the reason that you must put. You must say, okay, I see that AT equals to BT, and the reason is that these are the tangents drawn, okay, tangents from the same point, equal. You leave it there, right? There's another theorem that I want to add. It's not really a theorem. It's a result. I spoke about this in the beginning, that if you have a tangent of a circle, and then that tangents meet the radius of a circle, then the two will make an angle of 90 degrees, right? This is very important, right? So if I have a tangent drawn and then I have a radius, remember a radius is any line that is drawn from the center of the circle to the circumference. So a radius and a tangent at that particular point where they meet, they make an angle of 90 degrees. They make an angle of 90 degrees. So if you were to find this as well, and then you want to use this result in your reasoning, this is the reason that you must use. We say tan perpendicular to radius. So this reason works for this portion where the tangent is perpendicular to the radius, right? Let's look at our example 6 now. That jumped very fast, okay? Now, we are required to calculate the value of x here. I'll tell it to you that AT and BT are the tangents of the circle, right? And then you have the radius OA and radius OB. Now you are required to calculate the value of what? Of x, right? We have just shown that the tangents drawn from the same point outside the circle are equal in length. That means AT equals to BT. They are all equals to 4 centimeters. So we can show that, okay, BT equals to AT. These are tangents from the same point, right? And then there is another result that we have. We said a tangent and a radius at the point of contact, they give us an angle of what? Of 90 degrees. So we've just shown that OB is perpendicular to BT, tan perpendicular to radius, right? So we have 90 there. We have 3 centimeters, we have 4 centimeters, and we have x. Now x is the length of OT, even if it's not mentioned here. Length is, x is the length of OT. So if you look in this triangle OBT, we have a 90 degrees, we have 3 sides. Then we can use the theorem of Pythagoras to calculate the value of x, and the value of x is 5 centimeters there. So you see how this theorem may come in handy. All right. Let us move to the last theorem. Theorem 7, the Tan-chord theorem. This one, it's the popular one. When it's not, if it's not popular now, you get to know it because everybody seems to know it, right? It says the angle made by the tangent to a circle and a chord at the point of contact, it's equal to the angle subtended by the chord in the other segment of, right? So what that means is if I have a tangent and I have a chord, right? Let's start with chord AB. I have a tangent, I have a chord, and they meet here. So the angle that they make together at that point where they meet is the same angle, is equals to the angle that is subtended by this chord at the circumference. So if I was to follow this chord to the circumference, this angle that I find here would be equals to that. Similarly, if I have chord AC, you look at chord AC where it meets the tangent, this angle that is made here, if I was to follow this chord to the circumference, the angle B there, right? So that's what this theorem is saying. It says that the angle BAN, these are the red ones, BAN equals to the angle ACB, right? And then also the angle TAC equals to the angle ABC, right? Okay, there is a converse to this theorem. We use this converse to prove that something is a tangent. Just like what we did with the cyclic quad, sometimes you may be given, you may be asked to prove that something is a tangent to some imaginary circle that is not there. Because what is important about the Tan-chord theorem is for you to be able to note that this triangle here, the triangle ABC, all its vertices must touch the circumference of the circle for it to be a Tan-chord theorem. So it doesn't just work anywhere. You don't just find a tangent and some triangle and then say, okay, this angle equals to that. That's not how it works. All the vertices must touch the circle. So in a problem, you find there is a triangle whose vertices are touching the circle, and there is a tangent that touches one of the vertices there, right? Then obviously you have a Tan-chord. Nobody will tell you it's a Tan-chord. You need to be able to see that. So, but now there comes a time when they give you a shape where this triangle, where the vertices of this triangle are not touching the circle, and they want you to prove that it is a cyclic quad, right? This is the converse. So if you find that problem, the issue of the triangle will always be there, and some line would be there touching one of the vertices of the triangle. So it doesn't need to be P. It could be going this way, it could be going that way, it could be going this way, it doesn't really matter. Or it could be going this way. So there will be a triangle, right? So all you have to do is to show that this angle made by the tangent and the chord equals to the angle subtended by the same chord in the alternate segment, right? So if you show that this angle equals to that, then you have proven that PS is a tangent. And the reason that you give for that, you can just simply write converse Tan-chord theorem. And this is what I found being used in most question papers, right? They simply summarize it by saying converse Tan-chord theorem. I'll repeat this again. You find that this PQR is not in a circle. Remember, it must be like, if you look at this, all the vertices of this triangle must touch the they must touch the circumference of the circle in order for this to be a Tan-chord theorem. But in some cases, when they want you to prove that something is it's a tangent, you find that the triangle that they are referring to, because they'll tell you, okay, prove that PS is a tangent to a circle through PQR. You look at PQR, this triangle, the vertices of this triangle are not touching the circumference, right? So that's where you just have to show that this angle equals to that. If you do that, then you can say, therefore, PS is a tangent. What is the reason? Converse Tan-chord theorem. Let's look at an example to show you how this works, right? In this example, we are given that Tan is a tangent. We are required to determine the value of x and y. And then problem 2 says if DA bisects BAC. It's very important to read statements because sometimes such is not shown. We are told that DA, this is DA, it bisects BAC, right? But what does bisects BAC mean? The angle BAC, you see the angle BAC. So if DA bisects BAC, it means that A2 equals to A3. It means that the line DA cuts the angle BAC into two equal halves. That means A2 will be equals to A3, right? If this is 10, that will also be 10 degrees. If this is 20 degrees, that will also be 20 degrees. That's what is important here for you to see. Okay, they would want us to show that something is a tangent. But let's start with the first one. We have to find the value of x and y, right? X is there. This is our tangent. The question says, okay, the theorem says, if I have, okay, I find that, okay, I have this triangle over here, which all of its three vertices touch the circumference of the circle, and I have a tangent, and they meet here, right? So it means that this angle made by the tangent and this chord here should be equals to that angle over there, right? So which means our x equals to 80 degrees. It's Tan-chord theorem, right? Similarly, this triangle ABC touches all the vertices touch the circumference, and the tangent, of course, touches this point, and we get the angle y. So y will be equals to 40 degrees, which is the Tan-chord theorem as well, right? Now let's go to number 2. Number 2, we are required to prove that DA, this line DA, okay, sorry, we are required to prove that DC is a tangent to a circle through CEA. Okay, I want you to see this. We are required to prove that the line DC is a tangent to a circle through CEA. Look at this triangle that we are being given here. This triangle does not go through, okay, only C and A are touching the circumference of the circle, but E is not touching the circumference of the circle. Even DC is not a tangent because it's not out there touching this bigger circle. So this is what confuses most students or learners when it comes to proving these kind of problems, because now they look at it, how can it be a tangent? Fine. So all you have to look at here, okay, you have this triangle of which they want you to prove that this line is a tangent to it. So what do? Remember that theorem that I showed you? You just need to show that C1 equals to A2. C1, look at this triangle, right? Just need to show that that equals to that. Right? If you can show that C1 equals to A2, then we'd have proven that this is a tangent. Therefore, this is a tangent, right? We are required to show that C1 equals to A2. This is what is the crux of the matter here, right? How do we prove that? We know that C1 equals to A3. C1 equals to A3. Why? These are angles in the same segment. Look, we have the butterfly, which touches, and then all the vertices of this butterfly touch what? The circumference of the circle, right? So C1 will be equals to A3. These are angles in the same segment, theorem 4, right? So we are using theorem 4 now to prove something else. We know, okay, this C1 will be equals to A3. These are angles in the same segment. This is theorem 4. Also, we know that A2 equals to A3. We were told that DA bisects the angle BAC. So A2 will be equals to A3 because it's bisected by DA. Now we have a situation where C1 equals to A3, A2 equals to A3. Obviously, if A3 is 10, therefore C1 is 10 and A2 is 10. So the two will be equal to each other because they are both equals to A3. Right? So we have shown that A1 equals to A2. I mean C1 equals to A2. Therefore, this is a tangent to the circle. The reason? Converse Tan-chord theorem. Now we have exhausted the first 7 theorems that are covered in grade 11, right? So the next phase is to deal with exam type problems. These are the type of exam questions that you are most likely to encounter. So I've sourced these questions from the previous question papers. Let's go through them together. Let's start with problem number 1. In this problem, we are told that O is the center of the circle. We are given that AB is a tangent through the point A, and BC is a tangent through the point C. And then we are told that AD equals to DC. Extra information says that AC, where is AC? This AC is 8 centimeters. OD, this is OD, is 3 centimeters. B is X, where is BE? Also from here to here. So X is not for the whole, it's only for BE. And then AB is X plus 4. The first question, they say write down the size of angle D1 with a reason. So you just write down, there is no calculations here. This is the angle D1, right? This is theorem number 1. Can you see theorem number 1? I have a line drawn from the center of the circle to the midpoint of a chord AC. You see the chord AC. So it's a line that moves from the center of the circle to the midpoint of the chord. This is the converse of theorem 1. We said if we draw a line from the center of the circle to the midpoint of the chord, then that line is perpendicular to the chord, right? So this is how you should be able to see these theorems inside riders so that you can solve problems. So the first one, we see that D1 will be 90 degrees. Why? A line from the center to midpoint of the chord. This is the converse of theorem 1, right? And we can now use the theorem of Pythagoras, of course, to find the value of A. One other thing that we have to now do, we know that AC equals to 8 centimeters. That means the whole of this is 8 centimeters. Then we can divide this 8 by 2, because now for the length of AD will be 4 centimeters, DC will be 4 centimeters, because these two sides are equal, but the whole length is 8, right? So we have 4 there. We've been given this side as 3 centimeters. We can be able now to calculate the length of OA, right? This is the second question. The second question says calculate the length of OA. We have 4 centimeters, we have 3 centimeters, and D1 is 90 degrees. We've just shown that. So we have a 90 degrees angle. Then we can use the theorem of Pythagoras, because we have a right angled triangle, right? So the theorem of Pythagoras, DA is 4 centimeters, and then OD is 3 centimeters. That gives OA as 5 centimeters, right? The third question says determine with a reason the size of angle A. So angle A would cover everything here, right? I said when we're dealing with theorem number 6, right? When we're dealing with theorem number 6, I showed you that a tangent and a radius, right? If you look at OA is a radius, it moves from the center to the circumference. A tangent and a radius at the point of contact, they make an angle of 90 degrees, right? Remember, we said that. So A will be 90 degrees, and the reason is tan is perpendicular to radius. Now we are required to calculate the value of what? The value of X. How do we calculate the value of X? Right? First, we can try to find the length of OB, right? We already have the length of OE. The length of OE is 5 centimeters. Remember, OE is the radius of the circle. The radii of a circle are equal. We found OA to be 5. That means OC will also be 5. centimeters, and then OE will also be 5 centimeters from the center of the circle to the circumference. That's a radius, right? So the radii of a circle are equal. Now, then we can show that OB, the length of OB, the whole of this OB, is given by EB plus OE. EB is X, OE is 5. So now we have this length. We've just calculated the length of OA as 5 centimeters, and then we are also given the length of AB. That is 90 degrees over there. We have just shown it here. So we can use the theorem of Pythagoras. We have 90 degrees, we have this side, we have the hypotenuse. So this is what we can do by substitution, and then find the value of X as 8 centimeters. All right, now let us look at problem 2. Here we are told that S is the center of the circle, PST is the diameter. So this PST is the diameter, that is the center of the circle. Remember theorem 3, the diamond shape, the angle at center equals to 2 times the angle at the circumference, right? Do you still remember how we measured the angle at center? So the angle at center would be the whole of this, right? It would be the whole of it. So the first thing that we need to get here is the angle along a straight line. Remember, the angles along a straight line, they add up to 180 degrees. So PST would be 180 degrees. Now to find the whole PSR, the whole of this angle, so we would have to add PST and x minus 8. So that would be, remember, PST is 180 degrees because these are angles along a straight line. You need to add that reason. Now we know that PSR is 2 times Q, or 2 times PQR. So that would be 2 times PQR because of the angle at center twice the angle at the circumference. This is theorem 3, right? So we can simply substitute the values. Then we get X equals to 84 degrees. So the only thing was for you to notice the angle at center towards the angle at the circumference theorem, and also be able to remember that the angles along a straight line, they add up to 180 degrees, so that you can use the whole of that as the angle at center and then twice the angle at the circumference. Let's look now at problem 3. In problem 3, we are given that ABCD is a cyclic quad. Even if we were not given that statement, ABCD is a cyclic quad because it's a 4-sided figure and all the 4 corners or vertices, they touch the circle. So obviously this is a cyclic quad. We are also given one important information here, that AB, this line AB, is parallel to the line CD or DC, and we have D3 equals to 3 is equals to X. D3 equals to X is given to us here. The first question, 11.2.1, we are required to show that MC equals to MD. So each time you find a question like this where you are asked to show that one side equals to the other, remember the isosceles triangle, right? So what they want you to do, basically, if they want you to show that this side equals to that side, they just want you to show that this angle equals to that. Remember that the base angles of an isosceles triangle are equal, and we also know that the 2 sides of an isosceles triangle are also equal. So if MC equals to MD, that means D3 equals to C2. So now when they want us to show that MC equals to MD, they just want us to show that D3 equals to C2. So let's go about doing it. Let's show how these 2 angles are equal, right? Let's start with C2. Now C2 equals to A. Let's look at this. We have a cyclic quad which we're given, and then we have a line that extends ABCM, this line. So we have an exterior angle here of the cyclic quad. An exterior angle equals to the opposite interior angle. So A, Z2 equals to A. Because of that, again, we have D3 equals to A. D3 equals to A because we were told here that AB is parallel to DC. You have this F here. These are the corresponding angles, right? So we have corresponding angles because AB is parallel to DC. D3 equals to A. So you have these two angles, C2 equals to A, D3 equals to A. Now suppose A was 30 degrees, right? It means that C2 is 30 degrees, D3 is 30 degrees. Therefore, C2 or D3 equals to C2 because they are both equals to the angle A. Now we have just shown what they wanted us to do. Remember, we said that to show that MC equals to MD, you simply have to show that the base angles there are equal, right? So sides opposite equals angles are equal, and then of course angles facing equal sides are also equal. So therefore MC equals to MD, the base angles of the triangle are equal. 11.2.2 want us to determine the value of M in terms of X, right? So if you look in this triangle, CDM or MCD, we have D3, its value is X. D3 equals to C2, we have just established that here. So that means this is X and that is X in this triangle. So the only one that is missing is M. But we know that the sum of angles of a triangle add up to 180 degrees. So these are angles of a triangle, right? They add up to 180 degrees. We can simply substitute the value for D3, the value for C2. Therefore, M will be given by 180 degrees minus 2x. So we were able to express M in terms of x. It's 180 degrees minus 2x. Hence, 11.2.3, hence show that BODM is a cyclic quad. Remember what we did in Theorem 5 to say that to prove that something is a cyclic quad, there are three conditions. And these three conditions, of course, will be dictated by the type of shape that you are given, right? So if you look at what we have, they want us to prove that BODM is a cyclic quad, this one here, right? And like I told you, normally when they say prove that something is a cyclic quad, you find that it is not inscribed in a circle. If you look at BODM, the M is outside the circle already. The O is at the center. So this, you can't just look at it and say it's a cyclic quad because it's not inscribed inside a circle. The vertices are not within a particular circle. But now you need to show that it does have the characteristics of a cyclic quad. What are those characteristics? That the exterior angle equals the opposite interior angle, or that the opposite angles add up to 180 degrees. They are supplementary. So if you can show that the opposite angles are supplementary, or the exterior angle equals to the opposite interior angle, you would have shown that this is a cyclic quad, right? Also, if you could show that angles in the same segment are equal, but well, with the shape that they give us here, we can't actually use that here. We don't have the butterfly shape, so there's just no way we can do that. Now, the exterior angle part, we only have one. You see, D1 is if we can show that D1 equals to OBM, right? This and that. And if you check, we really don't have enough information to do that. It could take much longer to achieve that, right? But we already have the value for M, and we can find the value for O, right? So if we go O1 plus, if we start with O1 will be equals to 2x. Why is O1 equals to 2x? O1 equals to 2a. Is the angle at center. Look, this is the angle at center theorem, right? This is the angle at center theorem because this is the center. So the angle subtended by arc arc BD here at center will be equals to the angle subtended by the same arc, twice the angle subtended by the same arc at the circumference. We know that A equals to D3, D3 equals to X. That means A equals to X. Here, D3, C2, right? That means O1 equals to 2A, which is 2X. We already have M. M is 180 degrees minus 2X. So we are trying to add these two angles which are opposite to each other and see if we can get 180 degrees. If we add the two angles and they give us 180, then we have a cyclic quad, right? So if we add O1 plus M, 2x plus 180 degrees minus 2x, they give us 180 degrees. Therefore, we can claim that BODM is a cyclic quad because the opposite interior angles are supplementary. You need to also show that reason when you prove that. Let's move on to another problem. In this problem, we are given that the line KN bisects LNR. So what this statement says to us is that this line cuts this angle N into two equal halves. The other half is 25 degrees. So that means N1 will also be 25 degrees. That's what that statement is saying. 9.1, it says prove that Ln is the diameter of a circle passing through LMN. We want to prove that Ln is the diameter of a circle passing through LMN. Now, how do you prove that a line is a diameter? Remember the special case of Theorem 3, the angles in the same segment. We said that the diameter of a circle subtends an angle that equals to 90 degrees at the circumference, right? So if we are to prove that this Ln is a diameter of a circle that passes through LMN, we just need to show that M1 is 90 degrees. This will be the angle subtended by this diameter at the circumference, if you remember the special case of Theorem 3, right? So if we can show that M1 equals to 90 degrees, we would have shown that Ln is the diameter to that particular imaginary circle. Let's go about doing it, right? You know that O3 here will be 90 degrees. So what we are trying to do, I already have 25 degrees here, and I know that I can get the angle O3 in this triangle, you see. So I want to use the properties of this triangle in order to find the value of M1. So I have 25 there. I know that I can get this O3 by using the vertically opposite angles. I know that O3 will be equal to 65 degrees because these are vertically opposite angles, right? So if you have two straight lines that cross each other, this angle will be equal to this, and this will be equal to this, and then those are vertically opposite angles. And now once I have that O3 is 65, so I can add these three. I know that the sum of angles of a triangle add up to 180 degrees. So if I add M1, O3, and 25 degrees, I should get 180 degrees. This is the sum of angles of a triangle that gives M to be 90 degrees. Now, I have shown that M equals 90 degrees. Therefore, Ln is the diameter to the circle because it subtends an angle of 90 degrees. That chord subtends an angle of 90 degrees. Therefore, it is a diameter. 9.2, they want us to determine the size of angle L. So angle L is L1 plus L2, the whole of that, right? There are many approaches you could use to do that. What I want to use is the properties of triangles, right? I've got enough information to work with triangles here, right? So the first thing, if you look at K1 here, K1 will be 65 degrees. These are the base angles of this isosceles triangle. LK equals to LO, so therefore this will be 65, right? And I already have this angle is 25 because KN bisects this angle. So this will be 25 and that will be 25. So I have this angle, that angle. I can use the sum of angles of a triangle to find that. K1 is 65 degrees because LK equals to LO. N1 equals to 25 degrees because Kn bisects L and R. And therefore, I can use the sum of angles of a triangle just to find the value of L. L in that case would be 90 degrees. So the whole of that angle is 90 degrees. 9.3, they want us to show that this line LN is a tangent to a circle LMR. Remember the converse of theorem 7, the Tan-chord theorem, right? We said if you are given a triangle and some line that touches there and they want you to prove that that line is a tangent, all you have to do is to show that this angle equals to that angle. You need to show that the angle made by this line that's supposed to be a tangent and some chord there equals to the angle subtended by that chord in the alternate segment, right? In the alternate segment. So we just need to show that L1 equals to R. If we can show that L1 equals to R, then we would have proven that Ln is a tangent. Right? Now, I want to find the value of R here. How do I do that? I look at this bigger triangle. Remember, all the answers that you find in the previous steps, they apply as you move forward. So every answer that we find for 9.1, 9.2, we can continue using those as true as we go on, right? So I have this bigger triangle, the triangle LRN. This is 50. We have shown that N1 is 25 plus 25. This will be 50. We found the whole of L to be 90 degrees here. Therefore, we can find R in that case. We know that the sum of angles of a triangle add up to 180 degrees. Our L is 90 degrees. We have shown that. Our N is 50 degrees. Therefore, R will be 40 degrees. So we have found that R is 40 degrees. Now we need to find the value of L1. Right? How do we find the value of L1? Look at the triangle LMN. See how I just use the properties of triangles to solve these problems, right? The sum of angles of a triangle. So you look at the triangle LMN. I have N is 50 degrees. I have M1 is 90 degrees. Remember, we have proven that here, right? And then this is 50 because it's 25 plus 25. Then we can find L1 in that case, right? Using the sum of angles of a triangle, and then L1 is 40. So now we've shown that L1 equals to R. They are both equals to 40. Therefore, Ln is a tangent to that circle. And the reason that you give is that the converse Tan-chord theorem part. The last question says, is LR a diameter to the circle LMR? Is LR a diameter to this circle? Right. How do you prove that something's a diameter? It must subtend an angle that equals to 90 degrees. So in other questions, they are asking, is M2 equals to 90 degrees? Right, we have already found M1. M1 is 90, so angles along a straight line add up to 180 degrees. So if this is 90, obviously this is 90. So our answer will be yes. Yes, because M2 is 90 degrees. That chord here, it subtends an angle that equals to 90 degrees. Therefore, LR is a diameter to that circle. In this problem, we are told that O is the center of the bigger circle. We are also given that O1 is 2x. And then the first problem says, find 4 other angles that are equals to x. Right? We need to find 4 angles that are equals to x. Now let's look at what we've been given. If you look at this STOU, right? This is theorem number 3. The angle at center twice the angle at the circumference, right? If you look at the angle at center twice the angle at the circumference. So S1 will be half of 2x. So S1 will be x. This is the angle at center twice the angle at the circumference. Again, if you look in the bigger circle, this bigger circle, you look at this, we have this butterfly shape where all the vertices touch the circumference of the circle, right? This is theorem 4, angles in the same segment. Therefore, V3 would be equals to S1 would be equals to x, right? So V3 equals to x. These are angles in the same segment. Now, let's look into this smaller circle, the smaller circle, right? We have this butterfly as well. Do you see it? That all the vertices touch the circle. V3 is x, therefore W1 will also be x. Angles in the same segment. Let's look at angle O1 here. O1 is an exterior angle of this triangle OUV. You look at this triangle. So this is an exterior angle. That means O1 is given by V3 plus the whole of U, right? But why are we choosing this? We're choosing this because we already have the values. I have 2x. I have V3 is x as well. So the only thing that will be missing here will be U, right? So if I add this is an exterior angle of which is equals to the sum of the opposite interior angles, the two opposite interior angles. O1 equals to these two. That is the exterior angle of a triangle. Remember, we have the exterior angle of a cyclic quad and then the exterior angle of a triangle. The two are not the same. The exterior angle of a cyclic quad equals to its opposite interior angle, just one of them. But for a triangle, the exterior angle equals to the sum of the two opposite interior angles. So it's the sum of V3 and the whole of U in this bigger triangle, right? Now we have values for O1 and V3, which means U equals to x. Now we were able to find 4 angles that are equals to x. It's U, it's W1, it's V3, and S1. 10.2, determine the value of W2 in terms of x and also give reasons. W2 is this. There are many approaches we could follow here, but let's look at this cyclic quad in the smaller circle. It is a cyclic quad because all the 4 vertices touch the circle O, W, V, U. It's a 4-sided figure whose 4 vertices touch the circle. We have the value of U, it's x. We have W1, it's x. So the only missing thing is W2, and this is what we're looking for. What we can do is use the opposite angles of a cyclic quad. U plus W1 plus W2 is 180 degrees. These are the opposite angles of a cyclic quad. Look, is this angle plus that angle. Now that angle is W1 plus W2, the whole of it, right? U is given by x, W1 is x, the only missing part is W2. Therefore, W2 will be given by 180 degrees minus 2x. The third one, they want us to prove that WS equals to WV. Remember the isosceles triangle. So every time you are asked to prove that this side equals to the other side, remember the isosceles triangle. So what is required of you to prove is to show that S2 equals to V1. Let's do that. We say S1 plus S2 add up to 90 degrees. Why? Because TOV is the diameter, right? O is the center of the circle, so the line that goes through the center of a circle from circumference to circumference is the diameter. And we know from the special case of theorem 3 that an angle subtended by a diameter at the circumference equals to 90 degrees. Therefore, S1 plus S2 equals to 90 degrees. S1 therefore will be 90 degrees minus x. Remember that we know the value of s1. S1 is x, so the only one that is missing is s2. So s2 will be, we take x to the other side, it will be 90 degrees minus x. So the only thing we have to do now is to show that also v1 is equals to 90 degrees minus x. We already have the value of w2, we have the value of s2, the only thing that's missing is v1. So we can use the exterior angle of this triangle, the triangle WSV, this one, and say we know that w2 will be equals to s2 plus v1, right? So it's w2 equals to s2 plus v1 is the exterior angle equals to the sum of the opposite interior angles of a triangle. We have values for w2, we have values for s2, we don't have values for this, and then we can simplify and find that v1, it's also 90 degrees minus x. Remember, we were required to show that ws equals to wv, but we know that this question wants us to show that the base angles of these are equal. So we were required to show that s2 equals to v1. We found s2 to be 90 degrees minus x. We found v1 to be 90 degrees minus x. Therefore, we have proven it that ws equals to wv. These are the sides opposite equal angles. Here's another problem, problem 6. In problem 6, we are told that QS and PR are diameters. QS and PR are the diameters to the circle. We are also given that Q1 equals to Q2. So these two angles are. Also another information that's not mentioned here, QP is parallel to RS, shown by these arrows. So these lines are parallel. Also S1 is 48 degrees. We are required to determine with resist the size of Q1, of R, of M1 in the first problem, right? So how do we find the size of Q1? Look at this angle here. This line, by the way, you need to take note, it's not a tangent. Don't use the Tan-chord here. This line cuts the circle in two places, so obviously it's not a tangent. But this line shares the same side with the cyclic quad. Do you see the cyclic quad here? PQNS. PQ cyclic quad PQNS shares this side. So this is an exterior angle of a cyclic quad. And we know that an exterior angle of a cyclic quad equals to the opposite interior angle. So we can show that by saying S1 equals to Q1 plus Q2. It's an exterior angle of a cyclic quad, right? We know the size of S1. S1 is 48 is given here, and Q1 and Q2 are equal, right? So we can actually express this in terms of Q1 only, right? Remember, we are looking for Q1, so we can express this as 2Q1 because they are equal. If this was x and this was x, we could just write 2x. So now we can express this simply in terms of Q1. Divide that, you get the value of Q1 as 24 degrees. Now we need to find the value of R. Let's look at this shape. We have the butterfly shape, theorem 4, the butterfly shape. Therefore, Q1 will be equals to R. These are angles in the same segment, right? Angles in the same segment. You could also show that S3 equals to P, angles in the same segment. But we are not interested in that. Now we need to find the value of M1. We have a line that's parallel to that. Parallel lines, remember, we already have the value of Q1 plus Q2. We know that Q1 plus Q2 here is 48. Q1, Q2, 48. So we already know that this is 48 degrees. That line is parallel to that. Look at this F here, right? M1 will be equals to Q. These are corresponding angles shown by this F, corresponding angles, right? So M1 equals to Q is 48. These are corresponding angles. Lastly, we are required to prove that ST is a tangent to a circle M and S. So there's an imaginary circle M and S. We are required to show that ST is a tangent. what is it that they want us to do here? Remember the converse of theorem 6, the Tan-chord theorem. All we have to do is to show that S1 equals to M1. But that is already done. M1 is 48 degrees, S1 is 48 degrees. Therefore, ST is a tangent to the second. We are told that QPR is a common tangent to both circles. QPR is a common tangent. So it's a tangent for this, it's a tangent for the bigger circle as well. And then EDRC is a tangent to the smaller circle at C, only the smaller circle at C, right? The first problem, name with reasons 4 angles that are equals to x. We are given that A1 is x, so we need to find 4 more angles that are also equals to x. All right, let's start with the interesting one. I have this line which is parallel to that. It may not have been shown here, but these arrows tell us that these two lines are parallel. Therefore, AD is parallel to BC. Let's follow this set here. All right. So A1 will be equals to C2. These are alternating angles, right? C2 will be equals to X. These are alternate angles. By just following this Z, all right, that will be equals to that. So C2 equals to X. Another one, remember this is a tangent. So a tangent and a chord in this bigger circle, at the point of contact, they give this angle subtended by the chord in the alternate segment will be equals to the angle that they make at the point of contact. Right? So P1 will be equals to A1. P1 will be X. P1 equals to P5. These are vertically opposite angles. I have this straight line crossing this straight line. So P1 will be equals to P5. Those are vertically opposite angles. You have this butterfly. All right, look at this butterfly. These are angles in the same segment. So A1 will be equals to E, which means E equals to X. Now we managed to get 4 angles that are all equals to X. We found C2. C2 is X. P1 is X. P5 is X. E is also X. Let's go to 12.2. In 12.2, we are required to show that angle EPA equals to x plus 1. So EPA is P7, right? You see this angle P7 here. It's x plus 1. Note that D1 equals to P7. These are angles in the same segment. Can you see that? The butterfly. So if I work with D1, the answer that I get for D1 will be the same as the answer for P7 because they are equal, right? So D1, because of these parallel lines, will be equal to C1 plus C2. C1 is Y, C2 is X. So I have X and Y. So D1, it's already X plus Y, right? So D1 is X plus 1, but EPA equals to D1. These are angles in the same segment. Therefore, we have proven what they want us to prove here, right? And then finally, they want us to find the numerical value of x plus y if DCTP is a cyclic quad. So they want us to use the properties of a cyclic quad to find the value of x plus y, right? What we can use are the opposite angles because we do have enough information. We also can use angles in the same segment here because we don't have the butterfly shape here, right? We really don't have it. And we can't use these two sides, add them up because we don't have values for this. But we do have x plus y here, and we have enough information here. The only thing that we don't have is P2. Right? We have P1 is x. We have P3. We can find P3 because we know P3 is equals to P7. These are vertically opposite angles. We have P7, so we also have that. Now look at P2. We are told that this is a tangent. and we also told that this is a tangent. So these are tangents drawn from the same point. Theorem number 6. Tangents drawn from the same point outside a circle are equal. Therefore, RC equals to RP. That tells you that C1 equals to P2. So P2 equals to Y. P2 equals to Y because of Theorem 6. Tangents drawn from the same point outside a circle. If now we have P2, P3, I said P3 is the same as EPA, or P7. EPA, P7. So it's X plus Y. Now we can simply add all this, right? This angle plus that angle should give us 180 degrees. These are the opposite angles of a cyclic quad. Remember, they told us that DCTP is a cyclic quad. So if we add this angle and that angle should give us 180 degrees. So I was looking for the value of P2 so that I can use the whole of this angle and add up with that angle to use the property that says the opposite angles of a cyclic quad add up to 180 degrees. Right? There we go. This X is for P1, this Y is for P2, which we just found here, X plus Y for P3, X plus Y for this angle C, right? All this should add up to 180 degrees. They are the opposite angles of a cyclic quad. When we add them up, we have 3x plus 3y equals to 180 degrees. Divide both sides by 3, you get x plus y equals to 60 degrees. Remember what we're trying to do here. We're trying to find the numerical value of x plus y. So x plus y equals to 60 degrees. Let's look at the last problem. In this last problem, we are told that O is the center of the larger circle. OP is the diameter to the smaller circle. And then NP is the tangent to both circles at P. We are required to prove that PR bisects ORN. What does bisects mean? That means PR cuts the angle R into two equal halves. In other words, we are required to show that R1 equals to R2. That's what they want us to show. So how do we show that? We know that in this triangle, if you look this triangle, P1 is X, N is 90. So to get that, this is 90 degrees. To get R1, using the sum of angles of a triangle, R1 would be 90 degrees minus X, right? And then now let's come to this bigger triangle. Right, let's come to this triangle. This is a remember this is a tangent. Tan-chord theorem. That means P1 will be equals to T1. So T1 will be equals to X from Tan-chord theorem. And then this angle here, RPT, that's P2 plus P3. That should be 90 degrees. It's angles in the semicircle because ROT or TOR, this line here is the diameter, right? A diameter subtends an angle that equals to 90 degrees at the circumference, right? So we have a 90 degrees there. So I have X, I have 90, therefore R2 will also be equals to 90 degrees minus X. So we have shown that R1 is 90 degrees minus X, R2 is 90 degrees minus X. So the two angles are equal. That means RP indeed, or PR, bisects ORN. Lastly, we are required to prove that ROS, the angle ROS, which is given by O1 and O2, ROS is given by O1 and O2, equals to PAT, the angle A here, right? PAT, the angle here. We want to show that PAT equals to this. Let's start with PAT. I have this cyclic quad. Why do I start with PAT? Because I have R2 and PAT, and they are in a cyclic quad. You see the cyclic quad. I don't need to be told it's a cyclic quad. I can see it's a four-sided shape in this bigger triangle, the bigger triangle. It's a four-sided shape whose vertices are all touching the circumference of the circle. Therefore, this is a cyclic quad. A plus R2 should give me 180 degrees. PAT plus R2 should give me 180 degrees, but I already have R2. So I chose these two because I have enough information, right, to find the missing one, which is PAT. So PAT will simply be 90 degrees plus X. So I have this now. All I have to show is that O1 plus O2 also give me 90 degrees plus X. The first part is that P3, this one, P3 here, look, like an OP and OT are the radii of the circle. The bigger circle, remember this is the center. A radius is any line from the center to the circumference, from center to circumference. So these are the radii of the circle, they are equal. You have an isosceles triangle, that is X. This should also be X. Let's try to find the value of O1. You see, O1, I could find it using the angle at center twice the angle at the circumference, but it might be confusing for others who might not be able to see how this works in this situation. I have this chord which subtends O1. The same chord also subtends T1, right? So it's the angle at center twice the angle at the circumference. But we could use the exterior angle of a triangle, right? I have this triangle and this side is shared, so O1 will be equals to T1 plus P3. O1 will be T1 plus, or P3 plus T1, which is 2x. Remember, P3 is x, T1 is x, so O1 will simply be 2x. Right? So even with the angle at center twice the angle at the circumference, O1 will still be 2x. The angle at center twice the angle at the circumference. Right? And then S1 is 90 degrees. This is the angle in a semicircle. Remember, we were told that OP is the diameter of the smaller circle. So OP is the diameter. A diameter subtends an angle that is 90 degrees to the circumference of the circle, the smaller circle. So S1 is 90 degrees. So in this smaller circle, I have X, I have 90 degrees. Therefore, O2 will be 90 degrees minus X. So these are sum of angles of a triangle. If I add O1 and O2, remember I'm trying to find the angle ROS. ROS is given by O1 and O2. Right? If I try to add the two, I get 90 degrees plus X. Therefore, the two angles are both equal because they are equals to 90 degrees plus